The height of the Cold War was a period defined by the search for the ultimate strategic high ground, which paradoxically led military planners to look toward the deepest and most hostile environments on Earth. In the late 1960s, the Boeing company, in collaboration with the United States Navy, began secret work on a concept that sounded like science fiction, but was pursued with deadly, serious intent. This was Project Spider, a proposal to construct a massive modular military base designed to operate on the abyssal plains of the ocean floor, thousands of feet below the reach of any conventional submarine. Unlike fixed underwater habitats, Project Spider was designed for mobility. The entire base was envisioned as a collection of interconnected titanium spheres mounted on colossal hydraulic walking legs. This allowed the facility to literally walk across the seabed, effectively disappearing into the lightless canyons of the deep ocean to avoid sonar detection. It was intended to be a nuclear-powered ghost city, moving silently through the dark, capable of launching missiles or conducting surveillance while remaining completely invulnerable to surface attack. Before we dive into the crushing pressures of this mechanical nightmare, please take a moment to hit the like button and subscribe to Never Built. We uncover the lost future that the world canceled. We promise you this: stick with us until the final segment, and you will learn the one specific, terrifying physiological experiment planned for the crew of Project Spider that involved replacing the air in their lungs with oxygenated liquid to prevent their bodies from imploding under the weight of the ocean. Here is why this ultimate symbol of deep-sea dominance was abandoned. The first, overwhelming obstacle was the hydraulic stability paradox. While the legs allowed for movement, the extreme pressure at 6,000 meters depth meant that even a microscopic leak in a hydraulic line would cause the system to fail instantly, or worse, turn the fluid into a high-velocity jet capable of cutting through the base's own titanium hull. The second inescapable hurdle was the abyssal sediment trap. The ocean floor is not a solid surface, but often a thick layer of soft silt and mud. Engineers realized that a walking base weighing thousands of tons would likely sink into the muck and become permanently stuck the moment it tried to take a step. Finally, the project was fatally wounded by the nuclear thermal signature. To power the walking mechanisms and life support the base required a massive nuclear reactor, but the heat generated by such a power source would create a glowing thermal plume in the cold, deep water, making the invisible base an easy target for thermal sensors. The engineering philosophy behind Project Spider was a direct response to the increasing vulnerability of land-based silos and surface fleets. Boeing's engineers argued that the abyssal plains represented millions of square miles of untracked territory. By creating a base that could move several miles a day, the military could ensure that its retaliatory capability was always in a state of flux, making it impossible for an adversary to target. The base was designed around a series of reinforced titanium spheres, each serving a specific function from crew quarters to command centers. These spheres were connected by flexible pressurized corridors that could withstand the immense bending forces of the walking movement. The walking mechanism itself was a marvel of mid-century mechanical ambition. Each leg was equipped with massive articulated feet designed to distribute the weight of the base across the soft seabed. However, the sheer force required to lift and move these legs against the external water pressure was astronomical, requiring a specialized hydraulic system that operated at pressures never before seen in industrial applications. The environmental pressure crisis was the defining technical challenge of Project Spider. At the intended operating depths, the pressure exceeds 10,000 pounds per square inch. At this level, even the strongest titanium alloys begin to exhibit strange properties, and traditional lubricants or seals fail completely. The base had to be built with a double hull design, where the space between the hulls was filled with a non-compressible synthetic oil to help equalize the pressure. However, this added massive weight and complexity to an already bloated design. Furthermore, The issue of maintenance in such an environment was unsolvable. If a hydraulic joint on one of the walking legs failed, there was no way for a human diver or even a remote-operated vehicle of that era to perform a repair. The base was essentially a one-way mission. Once it descended to the depths, it was either fully operational or a multi-billion-dollar titanium coffin. The psychological and physiological toll of long-term isolation in the deep sea was another area where Project Spider faced dark reality. The crew was expected to live for months in a world of total darkness, where the only view outside was what the base's high-intensity spotlights could penetrate through the murky water. To survive the pressure in the event of a hull breach, the Navy explored the concept of liquid breathing, where the lungs are filled with perfluorocarbon liquid. This would theoretically allow the crew to exist at ambient deep-sea pressures without their chests being crushed, but the psychological trauma of drowning in liquid to stay alive was considered too high a risk for a mission requiring peak mental performance. The isolation combined with the constant groaning of the titanium hull under pressure created a high-stress environment that threatened to break even the most hardened submariners. Finally, the strategic obsolescence of the project became clear as satellite technology and advanced sonar improved. The military realized that as sensors became more sensitive, the very act of moving a massive mechanical structure across the seabed would create a seismic and acoustic signature that could be tracked from thousands of miles away. The Spider would not be a stealthy predator, but a noisy, lumbering giant that could be easily intercepted by fast attack submarines. The cost of building and maintaining a single walking base was estimated to be higher than that of an entire fleet of traditional nuclear submarines, which offered better speed and similar stealth. By 1972, the funding was quietly withdrawn, and the blueprints for Project Spider were classified and buried in the archives. The dream of the walking deep-sea fortress died because the ocean floor was a far more complex and punishing battlefield than the engineers at Boeing had ever imagined. The second phase of Project Spider's development was characterized by the mechanical paradox of the hydraulic gate and the nearly impossible task of engineering a locomotion system that could function under the weight of an entire ocean. Boeing's engineers had to solve a problem that had never been faced in the history of land-based robotics: how to move a multi-thousand-ton structure through a medium that is 800 times denser than air while subjected to 600 atmospheres of pressure. The proposed solution was a high-pressure closed-loop hydraulic system that used a specialized, non-compressible synthetic fluid instead of standard oil. In the vacuum of the deep sea, traditional pumps would cavitate and fail almost instantly, so the system had to be entirely equalized with the external pressure. This meant that the hydraulic lines themselves were under such immense tension that any structural fatigue in the joints would result in a violent, explosive decompression that could slice through the base's support struts like a hot wire through wax. The silt displacement and foundation failure represented the most significant geological hurdle for the walking base. Military geologists discovered that the abyssal plains are not made of solid rock, but are often covered in hundreds of feet of marine snow, a fine gelatinous silt composed of organic detritus. When the massive circular feet of the Spider base would step down, they would not find purchase on a solid floor, but would instead trigger localized turbidity currents. The weight of the base would cause the silt to liquefy, potentially swallowing the legs up to the knee joints. To combat this, Boeing proposed a radical dynamic buoyancy foot design. Each foot was equipped with high-pressure thrusters that would blast water downward to create a momentary cushion of high pressure, allowing the foot to float above the silt as it took a step. However, the energy required for this maneuver was staggering, and the clouds of sediment kicked up by the thrusters would blind the base's external sensors for miles, forcing the crew to navigate blindly through a self-generated fog of mud. The nuclear heat plume and thermal detection problem turned the stealthy ghost base into a glowing beacon on the infrared spectrum. A walking base of this magnitude required a high-output nuclear reactor to power the massive hydraulic pumps and the internal life support systems. In the near-freezing temperatures of the deep ocean, the heat rejected by the reactor's cooling system would create a massive plume of warm water that would rise toward the surface. In the 1960s, the Navy began to realize that Soviet thermal imaging satellites and deep-sea sensor arrays could easily detect these thermal chimneys against the cold background of the deep. To hide this signature, Boeing planned to install long-range thermal diffusers, miles of copper piping that would snake behind the base to dissipate the heat slowly over a vast area. This added yet another layer of catastrophic mechanical complexity. If the base needed to make a quick maneuver or change direction, it would be tethered to its own cooling tail, making the entire structure as clumsy and vulnerable as a wounded animal. Beyond the external mechanics, the internal atmospheric toxicity and fire risk in a high-pressure habitat created a lethal living environment. Because the base was designed to operate at extreme depths, the internal air pressure had to be carefully managed to prevent the hull from buckling. This required an heliox atmosphere, a mixture of helium and oxygen. While this prevented nitrogen narcosis, it created a surreal and dangerous environment. Helium conducts heat far better than nitrogen, meaning the crew would constantly lose body heat to the air, requiring the interior to be kept at a sweltering 90 degrees Fahrenheit just to prevent hypothermia. Furthermore, in a high-pressure oxygen environment, the risk of fire is exponentially increased. A single electrical spark could turn a cabin into a localized sun in seconds. Every piece of equipment, from the navigation consoles to the crew's clothing, had to be made of non-flammable, specialized polymers, making the interior of the spider base feel like a sterile, high-pressure tomb, where even the slightest mistake could lead to an unstoppable inferno. The structural fatigue and creep of titanium at abyssal depths finally forced the Navy to reconsider the long-term viability of the project. While titanium is famous for its strength-to-weight ratio, at the constant crushing pressures of the ocean floor, the metal begins to undergo a process called mechanical creep, where the atomic structure of the hull slowly deforms over time. The massive spheres that made up the base would gradually lose their perfect circularity, becoming slightly egg-shaped. In a high-pressure environment, a sphere is the only shape that distributes stress evenly. Once that shape is compromised, the risk of a catastrophic implosion, a collapse so fast it occurs in milliseconds, becomes a mathematical certainty. The Navy's structural analysts concluded that the spider base would have a shelf life of less than 2 years before the pressure simply reclaimed the titanium as its own. This meant that for every base deployed, a multi-billion-dollar replacement would have to be built every 24 months, making Project Spider the most expensive and least sustainable defense project in the history of the United States. The third critical phase in the unraveling of Project Spider was the acoustic signature and seismic detection paradox, which effectively stripped the walking base of its primary strategic advantage, stealth. While the deep ocean was once thought to be a silent void where a mobile base could hide indefinitely, the development of the Navy's Sound Surveillance System, or SOSUS, proved that the abyssal plains were actually an incredibly efficient conductor of noise. The mechanical action of the spider base was a catastrophic failure in acoustic engineering. Each time one of the massive hydraulic legs lifted and slammed back down onto the seabed, it created a low-frequency seismic thump that resonated through the Earth's crust and the water column for hundreds of miles. To a Soviet hydrophone array, the spider base did not sound like a ghost. It sounded like a slow, rhythmic drum beat that could be triangulated with terrifying precision. Boeing's engineers attempted to mitigate this by designing massive acoustic dampening pads made of high-density polymers for the feet, but the sheer mass of the base made it impossible to move without creating a localized earthquake that any modern sonar could detect from across an entire ocean basin. The abyssal energy logistics and the problem of refueling a walking nuclear fortress presented a secondary layer of unsolvable complexity. While the onboard reactor could provide power for years, the mechanical wear on the walking joints required constant lubrication, and the specialized hydraulic fluid needed to be replenished due to microscopic high-pressure leaks. This necessitated a deep-sea resupply infrastructure that simply did not exist. The Navy would have had to develop a fleet of specialized cargo submersibles capable of docking with a moving base at 6,000 meters depth in total darkness. The docking procedure itself was a nightmare of precision engineering. The two massive structures would have to align their hatches within millimeters while subjected to shifting deep sea currents and the unstable footing of the silt-covered floor. If the docking seal failed for even a fraction of a second, the pressure differential would cause an instantaneous implosion that would destroy both the resupply craft and the walking base hub in a single violent event. The biological interference and biofouling in the deep sea was an unforeseen factor that threatened the mechanical integrity of the walking legs. While the abyssal plains are often described as a desert, they are inhabited by specialized organisms in high concentrations of mineral deposits. Scientists discovered that the heat generated by the base's nuclear reactor and hydraulic pumps acted as an attractant for deep sea life and accelerated the process of manganese nodule accretion. Within months, the precision joints and hydraulic pistons of the walking mechanism would be covered in a layer of mineral crust and biological growth that acted like sandpaper. This abrasive layer would shred the high-pressure seals and jam the articulated joints, leading to a catastrophic leg seizure. A walking base with a jammed leg was worse than a fixed base. It was a tilted, unstable structure that risked tipping over into the soft silt, where the pressure would inevitably find a weak point in the skewed hull. The communication decapitation risk also plagued the project's strategic viability. To receive orders or launch coordinates, the Spider base needed to remain in contact with the surface command. However, at 6,000 meters depth, radio waves cannot penetrate the water column. The base was forced to rely on extra-low frequency ELF arrays or a series of tethered communication buoys that would float thousands of feet above the base. These buoys were the Achilles heel of the entire system. They were easily detectable by surface ships and aircraft, and if a buoy was severed or destroyed, the Spider base would be effectively blind and deaf, wandering aimlessly in the dark without any way to verify its mission or receive a launch command. This isolation created a terrifying scenario where a nuclear-armed walking base could be lost on the ocean floor, its crew suffering from psychological breakdown or mechanical failure, with no way for the outside world to intervene or even locate the wreckage. Finally, the internal life support and toxic buildup within the sealed spheres became a chemical ticking time bomb. In a high-pressure heliox environment, the removal of carbon dioxide and trace gases like carbon monoxide becomes significantly more difficult. Traditional chemical scrubbers were less efficient at 600 atmospheres of pressure, leading to a gradual buildup of toxic gases that would dull the cognitive functions of the crew over time. The slow poisoning of the crew meant that by the time a critical mechanical decision needed to be made, the engineers and pilots might be suffering from subtle hypoxia or gas toxicity, leading to fatal errors in judgment. The Navy realized that the Spider base was not just a challenge of external pressure, but a battle against the internal chemistry of human survival in a space that was never meant to hold life. By the time the project reached its final review in the early 1970s, the Spider was seen not as a weapon of the future, but as a multi-billion-dollar death trap that combined the worst risks of space travel with the crushing reality of the deep. The fourth and final phase of Project Spider's history is the silent legacy of its cancellation and the definitive realization that the abyssal plains are a frontier where human presence is best served by machines rather than manned fortresses. The termination of the project in the mid-1970s marked the end of the Navy's ambition to put boots on the seabed and shifted the strategic focus toward the development of unmanned undersea vehicles and more traditional fast-attack submarines. The cancellation was not merely a budgetary decision, but a profound admission that the laws of deep-sea physics regarding mechanical fatigue and hydraulic integrity were insurmountable obstacles for a structure of that magnitude. The Spider Base was the final attempt to treat the ocean floor as a terrestrial battlefield, and its failure ensured that the deep sea would remain a domain of stealth and sensors rather than walking iron cities. The industrial and scientific aftermath of Project Spider's collapse saw a massive transfer of specialized knowledge into the offshore oil and gas industry. The research Boeing conducted into high-pressure titanium welding and non-compressible hydraulic fluids became the foundation for the next generation of deep-sea drilling equipment and remote-operated vehicles, or ROVs. While the walking base never patrolled the ocean floor, the technology developed to keep its joints moving under 600 atmospheres of pressure allowed humanity to tap into energy reserves that were previously unreachable. The failure of the Spider Base was a catalyst for the unmanned revolution in oceanography, proving that it was far more efficient to send a small, agile robot into the dark than to attempt to shield a human crew inside a multi-thousand-ton walking coffin. The project transitioned from a military secret to an industrial blueprint for the exploration of the abyss. The structural and material legacy of the titanium spheres also provided a chilling dataset for the design of future deep submergence vehicles. The study of mechanical creep and long-term hull deformation under constant pressure changed how we evaluate the lifespan of every submarine in the global fleet. The project proved that there is a definitive limit of occupation for manned structures beyond which the integrity of the metal itself becomes the primary enemy. This realization put an end to the dream of permanent abyssal colonies and led to the current doctrine of short-duration deep dives, followed by extensive structural testing. Project Spider taught the engineering world that the deep ocean does not just attack the seals and the valves, but it slowly and relentlessly attempts to return the very atoms of the hull to their original state, crushing the ambition of anyone who tries to stay too long. The strategic re-evaluation of undersea dominance that followed the project's end led to a significant shift in Cold War naval tactics. Without the mobile walking bases, the Navy focused on perfecting the silent service of the nuclear submarine fleet and the deployment of massive static sensor arrays like SOSUS. The idea of the mobile walking fortress was replaced by the concept of distributed lethality, where smaller, more numerous assets are used to control the vastness of the ocean. The Spider was the last of the great machines of the 1960s, an era that believed in centralized, massive power. Its abandonment marked the beginning of the information age, in the deep, where the ability to see and hear from a distance became more valuable than the ability to survive a direct hit inside a titanium shell. The walking base was a prehistoric concept in a world that was rapidly becoming digital and transparent. Project Spider remains a magnificent and terrifying conceptual monument to the Cold War's willingness to challenge the most extreme environments on Earth. It was a project defeated by the intersection of geological instability, chemical toxicity, and the unyielding laws of thermodynamics. The decision to abandon the walking base was the moment the military realized that the ocean floor is not a place to be conquered, but a place to be monitored from afar. The Spider was designed to be the king of the abyss, a mechanical titan that would walk through the darkness, but it was eventually brought down by the weight of the water above and the softness of the mud below. It stands as a testament to an era when engineers were not afraid to build monsters to fight in the dark. The final question remains. Project Spider failed because it was too massive and loud for the sensitive sensors of the 1970s. Today, we have advanced carbon fiber materials and silent electric actuators. Do you believe that a modern version of the walking base could actually achieve stealth in the deep ocean? Or has the abyss become so transparent to sensors that there is truly nowhere left for a giant machine to hide? Join the discussion below and tell us, would you be willing to spend 6 months in a titanium sphere at the bottom of the ocean if it was the only way to ensure your nation's security? If you enjoyed this professional deep dive into the abandoned engineering of Project Spider, like this video and subscribe to the channel for more stories about the incredible projects that were never built.